You've been living inside time your entire life. Every breath, every heartbeat, every single thought you've ever had. It's all been wrapped in time. And here's what's strange. You've never once questioned what it actually is. Neither have I, not for a long time. We measure it, we schedule around it, we feel it drag on a boring afternoon and vanish on a good one. We built atomic clocks so precise they'd lose 1 second in 300 million years. We did all of that. And somewhere along the way, we convinced ourselves that measuring something is the same as understanding it. It isn't. Here's the thing nobody tells you. The more physics has figured out about time, the less time seems to actually exist. That's not a metaphor. That's where the equations lead. And I want to take you there, step by step, because the destination is one of the most genuinely strange places in all of science. Let's start with something that should bother you more than it does. Almost every fundamental equation in physics, Newton's laws, Maxwell's equations, quantum mechanics, general relativity, works equally well in both directions of time. Run them forward, run them backward. Mathematically, they don't care. The physics is the same either way. Think about what that means. Watch two billiard balls collide, then play the video backward. You can't tell which is which. Watch planets orbit the sun, reverse the footage. It's still valid physics. The equations have no preference. There's no forward baked into them anywhere. Now watch an egg fall off a table and smash on the floor. Play that backward. You'd know instantly. The broken egg leaps up, assembles itself perfectly, lands back in someone's hand. Nobody would believe it. Every cell in your body would reject it as absurd. But here's the problem. The particles in that egg obey the same time-symmetric laws as the billiard balls and the planets. So why does the egg know which way time goes when the equations don't? That gap between what physics says and what the egg does is one of the deepest unsolved problems in science. It has a name, the problem of the arrow of time. And the answer we found, such as it is, only makes the mystery bigger. The answer is entropy. The second law of thermodynamics says that entropy, a measure of disorder, always increases over time or stays the same. A broken egg has more disorder than a whole one. Smoke disperses into a room, never spontaneously reconcentrates. Heat flows from hot objects to cold ones, never the reverse on its own. This is why time seems to have a direction. The universe moves from ordered states toward disordered ones, and that movement is what we experience as time passing. That's the answer. Now here's why it's not really an answer. The second law isn't a fundamental law of physics. It's a statistical law. It describes what happens in practice because there are vastly more disordered states than ordered ones. If you let 1 million particles loose in a box, they'll spread out. Not because they have to, but because almost every possible arrangement they could be in is a spread out one. The concentrated arrangement isn't forbidden, it's just spectacularly unlikely. Here's the real question. If entropy always increases, it had to start somewhere low, and it did. The universe at the Big Bang was in an extraordinarily low entropy state, almost perfectly uniform, extraordinarily ordered, a kind of pristine cosmic smoothness. From there, entropy has been climbing ever since, and that climb is what we call the arrow of time. But why was entropy so low at the beginning? Nobody knows. Roger Penrose worked out the probability of the universe starting in such a low entropy state. The number he got was 1 in 10 to the power of 10 to the power of 123. That's not just a big number. Writing it out would require more zeros than there are atoms in the observable universe. It's a number so incomprehensibly improbable that calling it a coincidence feels like a category error. The arrow of time exists. Its origin is unexplained. Every time you try to grab the explanation, it points backward, back through entropy, back to the Big Bang, and there it stops. A shrug in the mathematics. An astonishing fact that just sits there without a reason. And then Einstein showed up and made it stranger. Before 1905, time was Newton's time. Absolute, universal, the same everywhere. One clock ticking for the whole cosmos. One now, shared by every object in the universe. It was such a natural assumption that barely anyone questioned it. Einstein ended it. Special relativity says time passes at different rates for objects moving at different speeds. Move faster, age slower. This isn't an approximation or a measuring artifact. It's real, and we've confirmed it every way possible. Muons are particles created by cosmic rays in the upper atmosphere, about 15 kilometers up. They're unstable. They decay in microseconds. At the speed they travel, they shouldn't survive long enough to reach the ground. But they do, consistently. because at near light speeds, their internal clock runs so slow, relative to us, that they survive the journey that their own brief lifetimes wouldn't otherwise allow. GPS satellites, the ones your phone uses to navigate, orbit at altitude and at speed. Both conditions affect how time passes for them. Without corrections for relativity, the clocks in those satellites would drift by about 38 microseconds per day. That sounds small. It isn't. After one day, your GPS position would be off by about 10 kilometers. Relativity isn't abstract physics. It's built into the device in your pocket. General relativity added gravity to the picture. Time runs slower in stronger gravitational fields. A clock at sea level runs measurably slower than one on a mountain. A clock at the bottom of a very deep well would tick slower than one at the surface. Gravity bends space-time, and bending space-time means bending time itself. The conceptual consequence of all this is one of the hardest things to fully accept. There is no universal now. Two observers moving relative to each other will genuinely disagree about which events are simultaneous, not because of signal delays, not because of measurement error. Fundamentally, there is no fact of the matter about which things are happening at the same time across distances. Simultaneity is relative. Now is local. The mathematics of relativity suggests something called the block universe. Space-time is a four-dimensional structure, past, present, and future, all equally real, all equally there, like different locations in space. The universe doesn't unfold through time. It exists, all of it, at once. Past and future moments don't disappear or arrive, they're just at different coordinates in the block, the way London and Tokyo are at different coordinates on a map. In this picture, time doesn't flow, it just is. And here's where it gets personal, because you are experiencing time flowing right now. This moment feels like the leading edge of something. The past feels gone, the future feels unwritten. The now you're in feels unmistakably real in a way the past and future don't. But the block universe has no preferred now. There's no equation for the present moment. There's no mechanism by which the moving sense of now, that felt sense of time passing, shows up in the mathematics. It doesn't. The flow of time is the most immediate feature of conscious experience, and physics has absolutely no account of it. Some physicists say the flow of time is an illusion, generated by the direction of increasing entropy. That's possible, but calling something an illusion doesn't explain where it comes from. Your brain is a physical system made of particles obeying time-symmetric laws. Why does it generate an experience that has a direction? Why does it generate experience at all? Those questions connect to the deepest mystery in philosophy of mind, and they brush up against the mystery of time right here. I can calculate where a particle will be at time t. I genuinely cannot tell you what it means for t to increase. I can't tell you why now feels like now. Quantum mechanics, when it enters the picture, makes everything stranger in a different direction. In general relativity, space and time are unified. Space-time, equally fundamental, woven together. In quantum mechanics, time is treated completely differently. It's a fixed external parameter, a backdrop against which quantum systems evolve. Time isn't quantized. It isn't an observable in quantum mechanics the way position or momentum are. It's just there, assumed, ticking away outside the theory. This is a problem because we need both theories. General relativity governs large scales, galaxies, black holes, the structure of the cosmos. Quantum mechanics governs small scales, atoms, particles, the behavior of matter at its finest grain. We've been trying for decades to reconcile them into a theory of quantum gravity, and one of the places they most stubbornly refuse to reconcile is exactly here. Their treatments of time are mutually incompatible. The Wheeler-DeWitt equation is the attempt to write down quantum mechanics for the universe as a whole. It's the equation that should, in principle, describe everything. And when you write it down, when you actually do the mathematics, there's no time variable, zero. The equation for the entire universe contains no time. Let that sit for a moment. The most fundamental equation we can write for reality doesn't include time. Carlo Rovelli and others have taken this seriously and proposed that time might be emergent, not fundamental, but something that appears at macroscopic scales the way temperature appears. Temperature isn't a property of a single molecule, it's what you get when many molecules interact. A single particle doesn't have a temperature. Maybe a single particle doesn't have a time either. The thermal time hypothesis puts it like this. We experience time flowing because we're complex, warm, high entropy generating systems deeply embedded in a thermodynamic process. Time, as we feel it, might be what the universe does when it's complicated enough to notice itself. And you, with your 100 billion neurons and your trillion synaptic connections and your intricate biology, are complicated enough. So you get time. A simpler system might get nothing, just quantum states, frozen, timeless, at the bottom of physics. Here's an angle that doesn't get made often enough. The reason you can remember yesterday but not tomorrow isn't a metaphysical mystery. It's a thermodynamic one. Memory formation is a physical process. To record information in your neurons, in a notebook, on a hard drive, you have to create a lower entropy record in a higher entropy environment. The act of forming a memory leaves a thermodynamic trace. The past has happened, which means entropy has increased, which means traces exist. Footprints in the thermodynamic snow. The future hasn't happened. Its entropy hasn't increased yet. There are no footprints. Your brain is a memory reading machine, and it can only read footprints that exist. The future made none, so you don't remember it. Causation works the same way. We think causes precede effects because we can only read thermodynamic records pointing one direction. Every intuition we have about time's direction, memory, causation, anticipation, the sense that the future is open and the past is fixed, all of it traces back to the entropy gradient. And the entropy gradient traces back to the initial conditions of the universe. And the initial conditions, we're here again, are unexplained. There's one more thing I want to say, and it's the hardest one. Every physical theory we have describes relations between events. This happened before that. This took this long. These were simultaneous in this reference frame. None of them, not one, describes a privileged present moment. None of them say, this is now. The present moment isn't in the equations, anywhere. And yet the present moment is the most certain thing there is. Whatever you think about the past or future, whatever you believe about physics or time or the block universe, you're experiencing something right now. That nowness, that felt immediacy, is the datum that all of science and philosophy has to account for, and neither has. Philosophers have three positions on this, and none of them are satisfying. Presentism says only the present exists, but that's directly contradicted by what relativity tells us about simultaneity. Eternalism says all times equally exist, the block universe, but then it can't explain why the present feels special. The growing block says the past and present exist, but the future doesn't, which is awkward and still can't explain why this moment, right now, feels like the leading edge of reality rather than just another point in the block. The hard question underneath all of this is the present moment a feature of reality or a feature of consciousness? If it's a feature of consciousness, then consciousness does something that physics cannot do. If it's a feature of reality, then our best physical theories are missing something fundamental. Either answer is extraordinary. I've spent my career working with time in equations. T equals this. T goes from 0 to infinity. Integrate over t. Differentiate with respect to t. Time is everywhere in physics. It's in every equation I've ever written. And I'll be honest with you, I have no idea what t is. It's the variable I've used most and understood least. And somehow that makes me more curious about it, not less. So let's be clear about what we actually know. Time is measurable with extraordinary precision. It's relative, affected by speed and gravity in ways we've confirmed experimentally. It's directional in experience, but symmetric in fundamental physics. It might be emergent, something that appears at macroscopic scales but doesn't exist at the quantum gravitational bottom of things. The deepest equation we have for the universe as a whole contains no time. The present moment, the thing you're experiencing right now, the most immediate and undeniable feature of consciousness, has no place in any physical equation. And what we don't know? What time actually is. Why it appears to flow when the equations say it doesn't. Why there's a present moment at all. Why the universe began in a state so absurdly improbable that our best estimate for the odds is a number that doesn't fit in the observable universe. Here's what I find beautiful about all of this, and I mean genuinely beautiful, not consolation prize beautiful. You are a time-experiencing thing in a universe that may not have time at its foundation. Your sense of the present moment moving forward, of the past being real and the future being open, of time passing as you read these words, all of that might be something your complexity generates. Not something written into the bedrock of reality, but something that happens when the universe gets complicated enough to notice itself. Time might be what it feels like to be as intricate as you are, and we don't know. We genuinely, honestly do not know. That clock on your wall, still ticking, still measuring. Underneath it, relativity warping its tick rate with every meter of altitude, entropy driving the direction of every tick, quantum fields at its foundation where no time variable appears, a block universe where all its ticks exist simultaneously, and a conscious observer experiencing each tick as the most real thing there is. The clock hasn't changed. Everything about what it means has. You've been moving through time your entire life. You still don't know what it is. Neither do I. And that, right there, that's not a failure of physics. That's where the interesting part starts.